All right, welcome. Today, we are putting your physics brain to the test with the Circular Motion Challenge. You think you know what really keeps a roller coaster glued to the track when it's upside down? Well, let's find out. So let's jump right in with a classic. Picture this. You're on a roller coaster. You're at the very top of a loop, completely upside down. What is that invisible force keeping you pinned to your seat? Go ahead, lock in your guess. The answer's coming up.
Okay, welcome to round one. We're going to start with the absolute foundation of all of this, understanding centripetal force. Let's get right into it.
So what even is centripetal force? Look, it's not some brand new magical force. It's just the name we give to the total force, the sum of all the forces like gravity or friction that's pulling an object toward the center of a circle. It's the force that makes things turn.
Okay, first question of the challenge. Based on what we just said, what's the name for the force that keeps any object moving in a circle? A, B, or C? What do you think?
And the answer is B, centripetal force. Now, this can be a little tricky because gravity and friction can be the centripetal force, but the general, all-encompassing term is centripetal force itself. If you got that one right, nice start.
All right, next up, this one is super important. In physics, direction is everything. So which way does the centripetal force always point? No exceptions.
It is always C, toward the center. In fact, the name centripetal literally means center-seeking. It's that constant inward tug that keeps an object from flying off in a straight line.
So let's do a little thought experiment. You're swinging a rock on a string, round and round. What happens at the exact moment that string snaps? Where does the rock go?
And the answer is C. It flies off in a perfectly straight line, tangent to the circle, right where it was when the string broke. This is just Newton's first law in action, right? An object in motion stays in motion in a straight line unless a force acts on it. The string was that force, and now it's gone.
Awesome job in round one. You've got the basic idea down. But now, let's add some numbers into the mix. Welcome to round two, where we get into the formula. And don't worry, it's actually way more intuitive than it looks.
And here it is, the big one. Centripetal force equals mass times velocity squared, divided by the radius. It might look a little intimidating, but this simple equation tells us everything we need to know about how these different factors relate to each other.
So let's just break it down real quick. Fc, that's the centripetal force we're solving for. M is the mass of the object. V is its speed, or velocity. And R is just the radius of the circle it's traveling in. Simple enough, right?
Okay, let's put that formula to use. Just by looking at it, if you make an object go faster, you increase V. What does have to happen to the force needed to keep it moving in that same circle? Does it go down, stay the same, or go up?
Of course it increases. This just makes sense, doesn't it? If you're swinging a bucket of water over your head, the faster you swing it, the harder you have to pull on that handle to keep it from flying away. The formula just confirms what we already feel.
All right, let's step up the difficulty a bit. This is where the formula gets really interesting. So a car's going around a curve. If the driver doubles their speed, say they go from 30 miles an hour to 60, how much more force do those tires need to provide to make the turn?
The answer isn't 2 times the force, it's 4 times the force. That's a huge jump. So what's going on here? Why 4?
The secret is right there in the formula. See it? F equals m times v squared over r. The velocity isn't just a direct relationship, it's squared. So if you double your speed, you have to square that number, 2, and 2 squared is 4. This single detail is so important for understanding why high speeds on turns can be so dangerous.
You're doing great. We've covered the concept, we've covered the math. So for round 3, let's put it all together and apply it to a real-world situation that trips a lot of people up.
So we're back on our roller coaster. You're at the very peak of that loop, totally upside down. The center of the circle is directly beneath you, toward the ground. Now think hard. What forces are actually pulling the car down, toward that center point? And the answer is C. It's actually both. This one messes with people. Obviously, gravity is pulling the car down, but the track itself is also pushing down on the wheels of the car. We call that the normal force. So you have 2 forces, both pointing toward the center, working together to make that turn.
Well, you've made it. This is the final challenge. We're going to put everything you've learned to the test with one last problem and one really critical real-world takeaway.
Let's do a quick bonus problem. Say you have a 2-kilogram object moving at 4 meters per second in a circle with a 1-meter radius. All we do is plug those numbers into our formula. So Force equals 2 times 4 squared. Well, 4 squared is 16, so 2 times 16 divided by 1. And that gives us our answer, 32 newtons. See? You can do this.
And that brings us to our final and maybe the most important question of the day. This is the real so what of all this physics. Using everything we've talked about, why is it one of the most dangerous things you can do in a car? To take a sharp turn at a really high speed.
And here's where it all comes together. We know that high speed requires a massive amount of centripetal force, all thanks to that v² part of the formula. Now, in a car, where does that force come from? It comes from only one place, the friction between your tires and the road. And here's the dangerous part. If the force your speed needs is more than the friction your tires can give, well, there's nothing left to pull you into the turn. Your car just keeps going in a straight line and you skid right off the road. So how did you do on the challenge? And maybe more importantly, will you ever look at a sharp curve the same way again?